Hello, am I audible?
Yes, sir. A very good afternoon, everyone, and welcome back to today's afternoon session. For this session, I am delighted to welcome Dr. Sudeep Roy as the speaker. Dr. Roy is an associate professor in the Department of Computer Science and Engineering at IIT Roorkee, where he also serves as a joint faculty in the Center of Excellence in Disaster Mitigation and Management. He completed his BSc in Physics and BTech in Computer Science from the University of Calcutta and later earned his MS by Research and PhD in Computer Science and Engineering from IIT Kharagpur. His research includes his research interests include electronic design automation for digital systems and microfluidic biochips, optimization techniques, and the use of ICT for disaster risk reduction. Dr. Roy has authored over 90 peer reviewed publications, hold multiple patents, and has received several prestigious awards, including the JSPS Long Term Fellowship, Japan, and the Early Research Career Research Award, DST, India, and the Microsoft Research PhD Fellowship. He is also a member of IEEE and ACM. Thank you, sir, for joining us today. We are truly honored to have you with us. I would now request you to kindly take over the session.
Okay, yeah. Thank you, Dr. Sanana Singh. Thank you for your kind introduction to the participants. So, very good afternoon to all of you. And as planned, so this session is on smart agriculture and will be taken by me and Dr. Akshay Pandey. So, I'll be starting with this uh, like this one. Yes. Thing. Yeah, this will come. Okay. So I'll starting the session with this topic like smart agriculture using IoT and AI based technologies like Internet of Things and artificial intelligence. So artificial intelligence is governing this email also. So I'll be talking about this how this these technologies like IoT and this AI are being used in this agricultural field so that the yield of the crop, the production of the crop, can increase, and also maybe it is ultimate goal is to basically to feed so many people as the population is getting high. So we need to meet the requirement also, the demand of food. So that's why agriculture is a very good, very important domain in which it is very much required now to intervene with these technologies, which are readily available with us. Maybe some of the things are already available, and some people are doing research to find out more, like this Internet of Things with the help of different sensors and satellites and all this. So they can basically monitor the agricultural field and agricultural means yield, and then apply their machine learning and this AI based techniques for data analytics, just based on this data. Those are collected by these sensors, and then means these are being used for the application development, like where this user, or maybe here in this case the farmers, are uh, able to see that what is basically the condition in their field in their own language, maybe that is easy to understand for the farmers, as well as maybe different kinds of natural language processing can also be done further. So this topic that I will be covering is going to introduce that what is smart agriculture, and then IoT intervention like Internet of Things at various stages of smart agriculture. I will be covering that in that next part. And then a survey of different smart agricultural system, like whatever people have done recently in the literature, we found, and where they are using this AI and machine learning along with this IoT. So we'll be talking about a last at the end that some of the development also in between that after doing this survey. So what we did in hydroponics, basically, in before I go to these application and foundations of this tiny ML. So tiny ML is, you can see that from the name itself. So this is ML, machine learning, but tiny. It is a small application. Okay, so this is not for the ML applications to run in the GPU. So it is just to run on the maybe Arduino board or in Arduino kit or maybe in the Raspberry Pi. Is a where this microcontroller or the microprocessor is very small capacity, or with the power processing capacity is low and the memory capacity is also low. So at the end, I will conclude this session. Sorry, for my part, and then hand over to Dr. Pandey. So the first introduction is that to improve the agricultural yield, we need different tasks. Like, okay, so just let me take the mouse pointer, so that will be better for you to, yes, laser pointer. So yeah, so for different agriculture, different problems, like in smart agriculture, what we basically talk about is basically to monitor the field by using some drone or UAVs, or maybe using the satellite images. And then the main challenges are here in two aspects. One is this disease prediction, so that when the plants are being implanted, and then they are not having the growth, and they're getting diseased and they're getting died. So basically, this is a basic, very big problem. So if we have some plan to help this many people's food to grow, and then all these are gone, then we'll be hungry. So that's why this is disease prediction is very important problem. And the second one is this irrigation automation. So this is depending on the water. So because when we are growing so much plant, so much lands of these crops, then we need a lot of water. But if you cannot monitor this, cannot control the water uses, so then we'll be having the scarcity of water also, right? So that's why this irrigation of water, or giving the water to the plants, should be automated. And this is a very big issue in terms of this, means all this current situation, like global warming and this climate change and all this. So that's why these two, most of the very, means all out of all the challenges, these two are main focus. And then at the end, like this sensors, so we'll be using some sensors for, people are using some sensors for predicting the disease or condition of the plant, and then also the requirement of the water in the field. So these are basically monitored by using some sensors. So after collecting this data, so these sensors are basically collected in a sensor data are being collected in a cloud, or in a cloud system, or maybe in a data center or in some computer. So there we need to do some analytics of the data, so that we can monitor these huge land sitting at some place, one small place, and then do all the things automatically. So that is requiring the smart analysis, and you can say that data analytics and the smart monitoring. So fewer the resources and labor, the effort that we want to reduce this resource and labor effort in this case. So by doing this automation, that's why we are calling this as a smart agriculture. And then plant cultivation and monitoring is required, and IoT-based architectures and platforms are the basic bone of this basic bone of this kind of system, smart agriculture. So agriculture is basically the prominent source of food. So that is why it is very important that we have already discussed. So new technologies and innovations like IoT, blockchain, ML, AI, data analytics, computer technologies, and big data, they play important role in this development. So that we can have this smart agriculture in reality, and then our farmers or our investors can start investing on this in this agriculture field. And more means automation will help us to give us this food. Basically, will not be hungry. So according to the Indian budget, if you see 2024 last year, so there was basically 1.5 lakh crore allocated for the agriculture and allied sectors. So it is a significant funding that could be allocated in R&D, means some R&D initiative also. So so in smart agriculture, so that is agriculture, well, farming and agriculture is basic of this human life and technology. So increase production and decrease extra manpower. So these are the main challenge, basically, main objective. So increase the production and decrease the extra manpower. So using IoT or Internet of Things, yes, and the wireless sensor network. Basically, you have a lot of sensors to deploy in the field or maybe near these plants where you're growing this, and then you have created some network which is wireless, and they can send the data through this network to the data center or to the cloud. So that basically maybe following operations can be supported if we can do this by using this IoT and this wireless sensor network. So that smart irrigation you can do that we have just discussed, and farm monitoring. So monitoring means it in terms of that how these crops are getting are growing, or maybe there is some disease attack or disease or some insects or some pesticides is required to be given. So control of fertilizers also. Sometimes the nutrients, those are being available in the water or in the soil where these plants are being grown, the nutrients are not sufficient. So we need to give some fertilizer. So we need some vitamins or something like minerals. So that's why we need to control the use of these fertilizers also. So another also that is soil monitoring. So we need to understand that what is the condition of the soil, how much nutrients are there, and so that we can add more nutrients accordingly. So all this requires some data collection and then decision making, and then apply some uh, uh, fertilizers or soil means you can say nutrients or maybe the water. So water quality monitoring and many more. So different applications are there so that we can achieve this smart agriculture. So agriculture is a crucial part of that we have already discussed, and IoT is the solution by automating this farming process and reducing this human effort and increasing the efficiency. So IoT, basically Internet of Things, uses the sensors that we have already noticed. So using the sensors and monitor the environmental factors like temperature, humidity, and soil moisture, right? So these are key parameters. So there are many more, not only these three, there are many more parameters to monitor or collect the data by using sensors. So enabling the precision irrigation and better crop management is the target. So by collecting and analyzing this data through this wireless sensor network, we can have this real-time monitoring system, which ensures that optimal irrigation is possible by reducing the water wastage and also enhancing the crop wealth. So that's why this disease prediction, the crop selection. So crop selection is also another task. I'll explain this later on. And field monitoring, like how these plants are growing and all this. Irrigation, that's water supply. Disease prediction is one thing. So let's discuss about this also. So crop selection. So like the area wise, what is the condition of the soil and the weather in that particular area? We can predict, we can suggest the farmers that this area you grow this kind of crop during this season. So season wise you can give the recommendation, so then you will get the more yield. So this kind of data, earlier there was no such system, so IoT and data analytics. So now we have a lot of data to collect, right? We have many sensors deployed already, and if once we have started with this setup, we started the collection of the data. So this will be the historical data for the future predictions. So then recommendation systems will work efficiently for the farmers so that they can achieve the most means you can say the productivity from the agricultural land. So supports this economic growth and sustainability in the agriculture also. So Internet of Things, what is this? You know that already, I guess. So that is networking of physical devices, right? So there are some physical devices which are consisting of some microcontroller or some micro processor connected with some sensors and actuators. So these are physical devices, and there is some networking that we have to build up. So data transfer, that means that the data can be transferred over this network without human to human or human to computer interaction. So automatic data transfer should happen. So from this IoT devices. So that is inherently a characteristic of this Internet of Things. So different components, when you are talking about this agricultural sector, so different components includes that different, there are sensors, there is a networking of the for the communication, and there are data that is being collected for the data analytics, and this built-in software. So some softwares need to be developed so that we can analyze those data and then achieve this application development. So human involvement is basically here requirement is that implementation and managing of this IoT system. So the focus is now moving to from this agriculture to IoT. So we need more skilled person who can develop this kind of IoT system and manage this kind of system rather than having these farmers. So farmers need to be trained in that case. So we can achieve a better society in this direction. So illustration here is a figure. You can see the tri-sectional sectional relationship between this human things and internet. So this is your internet of things. Role of IoT in agriculture. So if you think, we have already discussed about the soil management, this crop monitoring and control of the insecticides and pesticides. So this is another thing. Those to control this pest. Okay, so this is targeted pest control. So IoT can enable this by reducing this chemical use. So that is also important. So when people are using in nowadays in the farming land, so farmers are finding some insects are there in the crop in their crop. So they are putting their they're putting their insecticides or pesticides as much as they can. So there is no control over that. So this can be controlled based on the requirement of the of this insecticides and pesticides, so that we have less intrusion of this chemical. So when we are making the food, we will not have to take that chemical. So soil management that we have already discussed, the soil condition for better fertilization and the health of the crop. And this is water management, that is for the irrigation we have discussed. Crop monitoring means that in real time, we have to monitor the crop health. So how they are growing with time. So with time, they are growing, if you are thinking of this case, that plant is not growing like every second by some centimeter. So it is just like maybe every day a few millimeter or centimeter. So or maybe some in terms of some pixels, if we are using some image processing based techniques, so then we can think like that. So there are basically this a growth monitoring system will require sampling of the data by the sensors, that how these plants are being grown are means growing maybe means once in a day, or maybe means once in two days. So that may be the frequency of collecting the data. So then also after collecting the data, the analytics should be very fast, so that you can get the analytics results in real time. Okay, so that is the important thing here for crop monitoring. So the impact of IoT in agricultural resources, if you are talking about, so IoT is going to impact not only in the agricultural land by controlling this fertilizer, pesticides, water, soil, all this, but there are also other things like human resources. They are also reducing, and livestock also. Livestock means there's cows and this goats and all this, or yeah, hens. So these are all livestock, which animals. So they can also be monitored by using some sensors and all this. So that is called livestock monitoring, so which is also part of the agricultural sector. So another is this energy. So that is basically the we are talking about this use of battery or use of power of this electricity. So that can also be controlled or monitor. Means you can use the energy as and when it is required. So not like every time it should be switched on or something like that. So for the irrigation, we have seen that some kind of example is possible, that where the pump is not on for without any time given to that. So the technology infrastructure and the business relations are also there. And this is another thing, that is the seeds. So different kinds of seeds are also required for the for collection, as well as the how they are being stored, and they are also being used in the future for more crop growing. So moving to the next sector, next part, that is the IoT at various stages of this smart agriculture. So if we just have noticed that there are briefly I have discussed more, mentioned about these different sectors. Just going through this one by one. So soil sampling. So this is one. So soil is the stomach of the plants, right? So where this sampling is the first step examination to obtain the field specific information. So what is the presence of different minerals or the nutrients for the plant to be grown. So the plant wise, there is a requirement of this minerals also. So mostly this NPK, these are the main resources or minerals. Those are basically used. So N is the nitrogen and P is the phosphorus, potassium, sorry, phosphorus, and K is the potassium. So these are, and also manganese and magnesium, all these are also there. So different minerals are also there. So NPK. So this is there's a kind of sensors which are basically used for measuring this soil condition. So what is the nutrients available in the soil? Based on this, we can think of something that the farmers can be recommended that this kind of foods or maybe fruits or vegetables you can grow in your land. So there is a existing work that is named as agrocares, which was developed based on this idea, and this there is a lab in a box kind of system they have developed, which is basically soil testing kit. So I'll be discussing in some reference. I'll mention that later on. So the second one is this irrigation. So irrigation, just as we have just discussed, that various controlled irrigation methods are important. So like drip irrigation or sprinkler-based irrigation, or these are being promoted now to tackle this water wastage issues. So that's why this crop water stress index is another parameter, that is metric that is being used, that how much area of land you are having for this crop to grow and how much is the water requirement. So how will be the water stress index for that particular land. So these kind of indices are being developed, basically have been defined to monitor this, to make this irrigation management more precise, so that less amount of water is wasted. The third one is this fertilizer. So a fertilizer is a natural, or it can be chemical also. So chemical substance that can provide the important nutrients for the growth of and fertility of the plants, right? So now there is a index that is called NDVI. So this is based on the vegetation index, so development thing. And then it is basically calculated by using this from the satellite images. I think Dr. Pandey have worked on this, so he will explain more about this. So this is basically to monitor this crop nutrient status based on their growths, taking the image from the UAVs and the satellite images. So UAVs and satellites. So these is another thing that we can monitor the growth of the plant, and based on the growth and fertility condition, we can apply the fertilizer. The second, and also decide the quantity of the fertilizer to be applied. The fourth one is the crop disease and pest management. So what is this? This pest management involves that when there is some insecticides or pesticides, pest, so they need to be controlled by using these pesticides in providing this pesticides or the spray with a precise amount and very accurate one, so that there is no extra chemical that is being applied into the food or the crop. So that is very important thing also. So we do not want this not means we are now looking for this organic thing, right? So people are talking about this because we have understood that by applying these pesticides and insecticides, we are basically creating problems in our health while taking this fruit. So looking into the last one is that yield monitoring. So what is the yield? So yield means that given the area of the agricultural land, given the crop, so how much you can say that how much crop has been successfully you got some success, means you got some product, or you got some grains already successfully you got, and some you have wasted, so due to some reason. So dividing this total gain divided by the total area is giving you the yield. So now this is how to basically monitor the agricultural yield based on this UAVs on all this satellite image processing for a larger area. This can be thought of. So this is basically the data is being collected in the by the sensors like UAVs and satellites, and then their analytics are basically giving us this application. So overall, so this UAV farming, so nowadays we will be hearing that this IoT has invaded into the smart agriculture heavily for by applying different technological advancement happening through this UAV farming, UAV based farming in foreign countries and also in our countries nowadays. Different startup companies, different companies have started giving this facility, this kind of systems developed by them, and basically uh, helping the farmers. So monitoring the farms and then precise farming basically for different equipments those are being used. Monitoring the farm sitting at the home or at the remotely sitting at your house. The larger land can be monitored, and supply chain management also, like how this different product from the crop land will be used, and how this supply chain can be managed. This is a part of the business that is being developed based on the agricultural product. And there are different things like this analytics of the data and the prediction to make. And also this aquaponics farms has come up now as a new concept, because where this both plant and animal can reside together in that particular aquaponic system, where the waste of the animals will be used as the nutrients for the plants, and the waste of the plants will be used as the food for the these animals. So this is a very basically a balanced ecosystem to make for having this better growth of the plants. So these are the new concepts people are now developing and having some applications also based on this. So there are different sensors, basically major equipments if we are telling. So then there are different sensors we need, and maybe yeah, some are mentioned here, very few. So based on this paper in IEEE, so it's basically selected IoT based products and prototypes for the smart agriculture. So you can see that irrigation controller, seed or fertilizer, and soil sensor. So this is seed and fertilizer sensor or something like that. And there are different systems. You can see bug detector. So these systems look like this. There's something which is called this weather condition measurement. So there is a system which is basically monitoring the weather at that particular place. Harvesting robots. So these are also equipments which are used in smart agriculture, so that the harvestation can be harvesting the foods or fruits can be done easily without with less manual intervention. Next is this okay, so there are other things also. Crop health assessment, for that mobile app have been developed. So people are using mobile app to uh, take the picture of these leaves and then decide that what is the condition of the crop health. And there are also different kinds of sensors like this. You can see that leaf sensor to measure that what is the condition of the leaf of that particular vegetable, or maybe some monitoring robots which are used for spraying this fertilizers or spraying this insecticides or pesticides. And also there are something like this kind of sensor, that is stem size sensor, so which is basically used for measuring the stem size, so that we can understand that how the plant is growing with time, whether there is a hindrance in the growth or it is going fine. At the end, this spraying robots are also used for spraying these things. I think this I have mostly discussed. So there are different technologies which are being used in smart agriculture. They can be thought of as a different verticals. So in this paper, it is computer and electronics. I think I forgot the name of the journal. So this is the journal name. In 2023, they published this with some means category review. So this category is telling that what are the different technologies people have used for the smart agriculture. So main technologies in agriculture that involves IoT, blockchain, AI, machine learning, big data, and cloud computing and deep learning as well. In case of applications that we are discussing right now, before this was this soil monitoring, smart machinery, field monitoring, smart water management, irrigation, or something like that, satellite monitoring, satellite based monitoring, and smart zone seeding, so that where to put this deploy the seeds basically for the plant so that it can grow better way. Each and every plant can get saplings can get the sufficient space also. So, and also smart greenhouses. So people are talking about this smart greenhouses, because already we had some greenhouses earlier. So now making those as a smart greenhouses will help us to increase the yield of the production. The benefits include this this increasing the production, water conservation, real-time data and production insight, and also this increasing the quality of the production and other benefits. Like here also we can we have seen we just mentioned earlier that livestock farming. So we can improve the livestock farming by putting some sensors into the livestock animals, and we can monitor those animals, or people can monitor the animals by these systems. So they're developing this kind of systems also, so that the animals, whether they are lost or they are basically not feeling well, they are laid down or they are standing, or their health is good. So all these sensors are giving us the data at the remote place, and we can monitor. Means the farmers can monitor, or the investor can monitor the system, this livestock. So the emerging sub technologies, if you talk about, so then we are focusing on these different kinds of advancement of the robot. So making different kinds of robots, having all these facilities or different kinds of facilities, and purposing automation, and satellite image processing, even vertical farming is also now another technology. Like uh, since the space is horizontally, the space is shrinking because of this so much development. So you can also think of that vertical farming is also possible in our home garden. So RFID technology for making this ID for different systems, so that we can have this records for each and every plants or something like that. GPS technologies, these are basically emerging technologies. The different factors, if you talk about, so then soil factors is important for growth of the plant. Climate is very important for growth of the plant. So different type of sensors are required to be used, and analytics has to be done. Research is there to be done. A lot of work can be done here for different system, which is not a very general purpose, but at least for some spatial plants, or some which are very much important, like wheat in our country, or maybe rice, and some of the vegetables which are very popular, like potatoes and all these tomatoes. So for these different specific plants also, specific crop also, we can focus on different systems. So that's why research is going on in that direction for maintaining this data analytics part, along with this automation. And then this supply chain management and storage and all this are basically the second part. After this crop is grown and this harvestation is done, then how this is going to the business for the production, to increase the production yield. So here is the next one, that where part is talking about this irrigation. So smart micro irrigation management system, which is also, these are called as a services for the agriculture. So services means soil preparation. So you have a land where the soil is not good, so then you can recommend that you need to improve your soil by adding these things. So this kind of analytics has to be can be done by using the sensor data. And then the soil nutrients management also, and along with that different pesticides and fungicides to provide to improve the quality of the soil for fertilization, and also this crop yield condition monitoring, so that the yield can be increased. So ultimate objective is to improve the this crop yield, and by doing this smart agriculture. So there are different verticals that we have seen in the previous slide. Now, if we talk about a basic example of a smart agricultural system, so how it looked like. So there is a paper in last year it came. I have chosen some latest papers only. So you can look into these papers when you search. Okay, why this is coming. Okay, just a minute. So yeah, so the device the device is built to be cost effective and energy efficient and reliable. So whatever device we are talking about, so this is a smart agricultural device. Okay, so an example of smart agricultural device it is talking about, it should be cost effective. It should not be very high cost, right? It should be cheaper and it should be energy efficient. Like put these devices are working with battery, so we cannot change the battery very frequently, and reliable also. The system should not give very wrong results most of the time. So it will give most of the time the accurate results, and it will be resilient also, resilient to the temperature, weather, and all these things. So think about a system which is having different sensors like this: the moisture sensor, temperature sensor, humidity sensor, PIR motion sensor. So this is basically PIR motion sensor to monitor the motion of something, obstacles behind the in front of the object, and the smoke sensor to measure that whether there is some kind of different smoke. So these sensors are there, and there is a MCU. What is this MCU? This is node MCU. Is called the node microcontroller unit. And there's a specific kind of microcontroller unit that has been used here in this system. They are calling this system as a smart tech agri, and they are having this smart device like this. So having this MCU here, ESP8266. So this is a Arduino based system, Arduino based microcontroller, and this microcontroller can collect the data, all this data from the sensors, and process this data and connect to the internet also through this connection, and then send the data to the cloud platform. Okay. So if there is a requirement of buzzer to play for the smoke sensor, like there is a fire or there is some motion of something, some huge storm or something like that, or maybe some intruder has come. So these buzzers can be used for the actuator, as an actuator. There is a LED also. You can use this for for displaying something based on the input data that was collected from the sensors. So user input is also possible. Some system is there, and there is a power supply that is required, must be given to the MCU. So battery operated device. So this is a smart device, agricultural device, which requires these are the different components. So this is an example we can think of in the same line for different applications. Crop growth monitoring system, if we talk about, there is a journal paper came into in 2022. It talked about this kind of structure that is talking about there is a sensor network which is basically composed of different sensors. So each of these squares are the sensors, and there is a gateway node, which is a, you can say that, uh, which is basically the base station, and all the data are being collected from these different sensors are coming to this base station. Similar kind of structures are there also, and they're making a sensor network. So this sensor network is going to send the data to the, okay, so this is the base station, through the transmission network, and then this data can be sent to the remote server, or maybe user remote terminal can access through this user remote terminal. This data can be accessed to, which is actually stored in the remote data server. So this kind of hierarchical network type network development has been discussed. This is completely part of the computer network course. You can understand from the computer science department. So there are a lot of challenges for developing this kind of network. So different protocol, different network layers. At the different network layers, we have to do some developments, and then network congestion has to be handled in that case. So there are different issues related to computer network or network communication to build up this kind of monitoring system. There is another issue that is also, I'm just giving the glimpse of different problems, different means issues in the IoT based smart agriculture. So these are more generic right now, but will be going to be specific little bit also within the time limit. So the energy saving is another one, that we are using different sensors, right? So multiple sensors are being used. All the sensors are basically battery operated. Now, if these sensors are sampling the data from the crop field, So then they will be basically most of the time they will be, if they're sampling very frequently, then they will dissipate the power of their batteries, and then we need to replace them. So that's why, or maybe we have to recharge them. So that's why we need to be very cautious about deciding its mechanism, that how the sensor nodes will be used. So there will be some time where this sensor will need to be made active, and there will be some time, most of the time those will be at sleeping mode. Okay, so by managing this these modes of the sensors, we can efficiently monitor the data collection, or we can use the sensor network that is deployed by deploying this. These are the yellow dots are basically the sensors. So how they are deployed on the two-dimensional space in the 2D plane in the field. So how many sensors you will require, how they can be managed. So this is another challenge. Like this is a problem statement. I'm just explaining that how you can monitor these sensors, how they can be connected through the network, so that the energy savings is possible. Like you can have the maximum lifetime of the batteries uh, to make this whole network alive. Okay, so moving to more specific, some examples of smart agriculture using this AI and machine learning and IoT. So there is a particular system that is basically agri hydroponic system that was published in Journal of Network in 2022, where they talked about this IoT environment. Basically, with IoT environment, so there is a AI-based hydroponic system. So this is a hydroponic system which is talking about. I'll talk about hydroponics a little bit later. It is based on a system where basically the plants are grown with water only. So there is no soil. It is basically soilless. So there is a system where these plants are basically put there. I'll show that in the next slide. Like just talking about in terms of the smart expert system. Let's see, there are basically three phases. One is this, they're talking about this hardware part, that there is some hardware involved. So there is a Raspberry Pi, there are sensors, there are camera, there is actuators. So this is a hardware environment. There is some cloud part, that is basically the data has to be sent to the cloud. So there is some application software where we can run this classification model or prediction model, like in machine learning we do. So they are talking about this deep learning CNN, so hybrid DL CNN model. So they are applying there to classify these images, or maybe use some sensor data to predict something for future or some thing. So their mode of operations are basically decided based on this analytics. So the hardware can save the energy also. So this is basically agri hydroponic Android based application. There is a application which is basically having this access to the cloud, which is IoT cloud server. So there are basically three phases. One phase is talking about this hardware. Second phase is talking about this how this deeply learning convolutional neural network is working, how they are basically the software part. And the third phase is basically the farmers can monitor this data using this Android-based mobile application. So you can think about there's a kind of system like this. So I'm not going into detail of this particular paper. As I told, some of the sensors you can see here, they are mentioned here. So water pH sensor, turbidity sensor, water temperature sensor, air temperature and humidity sensor, sunlight sensor, and also NPK sensor, soil sensor, along with the camera to take the picture of the leaves. And then all this data has to be stored, and then basically some actuators are here. So screen for the data. So that will be showing this data collected. And some pumps are basically there for switching on and switching off by sending the signals from the Raspberry Pi. This is the MCU, microcontroller unit. And then there are different other sensors, other actuators also, like shade monitor or shade motor, or like you have to put the shade or not, cooler or to on or off, like this. So this is a system, overall system, how this hardware system looks like. There is a software part that is in the cloud. So there is a classification problem. There may be a prediction problem as well. So it is to estimate the perfect nutrient level based on the reference value. So that is a prediction model which can be used. So that is based on the data those are collected in the data set from these sensors, by the sensors. We can think of that different software models here. So in case of classification models, so you can identify different types of plants diseases presented in the plant images. So there are different plant images captured by those cameras, by the cameras, and then we can detect actually. Do I have any message here? Explain Raspberry Pi processor working. Okay, it will take time. So it's basically let me tell you just a few sentences. So Raspberry Pi is a microcontroller. So where this processor is there. If you have studied this computer architecture course, so we have studied in the within the processor there is a pipeline architecture or maybe some single stage pipeline or multi-stage pipeline where the instructions are written. So programs are to be written here for Raspberry Pi. We write the program using Python, and then this program is basically taking the input data, which is basically collected from the sensors. So when this program is written, is basically like this: that we activate some sensor pin, and then we sense the data at that time, and then process basically means that uh, analyze the data so that we can do the next task. So there is a whole lot of things. Basically, many means Raspberry Pi may collect multiple sensors data together and then process over that, or maybe based on one particular sensor data, it can generate some signal for activation or for activation of the actuators, or maybe the warning to create. Okay, so I think that was a harder part, and this is the software part. And then we have the mobile app also. In this particular paper, they are talking about that they have this mobile app to help the farmers to understand that what is the disease that particular plant is having. So just taking the using the camera, it is taking the image of the leaf of that particular plant, and then from the data set that is already there, trained model is there. By using those data set, they can predict that this is a kind of, so there may be hard, they have taken, I guess, 18 diseases, different 17 to 18 diseases, 17 diseases, and one is a zero disease, no disease. So these different classes they can classify based on the images they have captured. So yeah, so so the dashboard for the sensors for the agri hydroponics looks like this, where the farmers can see the values for different sensors they have used. So phosphorus, you can see potassium, air humidity, air temperature, water humidity, all this, and the mode of operation also. So manual mode or automate mode. So you can put this in automate mode, and then the actuators will be automatically automated by the means activated by the this Raspberry Pi. So the system looks like this, and you can see that there is an image of the leaf, and it is telling that tomato early blight. So early blight is the disease name for the tomato. Okay, so that basically is trained already. So disease detection from the cloud. So it is basically based on the ML application, ML program, that software that is running on the image that is captured by the camera. So already trained model should be there, right? Obviously. So those data basically collected initially, and then the trained model is created, and then this trained model is in the cloud to apply. Okay. So coming to the next paper here, it is talking about, okay, I think I have 10 minutes. Okay, so I can. So we can then monitor and control. So this is a part, this is an example of greenhouse. Okay, so in greenhouse we know that different crops can be grown with high yield with a specific control of this temperature, water, nutrients, humidity, all these things. So then there is a basically huge scope of in integrating IoT and this computer related processing techniques and data science, all this to make this more automated. So agricultural environment here is basically the this greenhouse, and there is architecture that they are showing here is a platform architecture basically. So there is a cloud in which they have this remote access to this cloud also, and the data are basically collected to this cloud by using some database where this stored data are being kept, and then this database can be sent to the cloud for further analysis, and HMI, that is human machine interface, is created where this data can be visualized, or you can see the analytics results can be visualized. And then also the decision making can be taken. So that is one particular application. So there is one more that is talking about this greenhouse effect. So you can say greenhouse system. So this one, okay, I think this is the same paper. Yes, this is the same paper. So this is showing that there are different sensors. Basically, temperature, humidity, these are the sensors. They are doing this RF communication. They can do this radio frequency communication to the sync node. They can send the data through this one. And then there is a Raspberry Pi board where this processing can be done with some database which is there in the cloud or something like that, through this hardware communication, through this router and Wi-Fi connections. And from the remote access, for the remote access, the PC and in the web application, or maybe some application can be developed in the smartphone or mobile app to access this data, as well as see the data analytics based on this data, and also give the decision result to create the comments by these Raspberry Pi to the actuators. So actuators can then actuate the fan on fan to be on, or maybe the valve for the pump. So water to give for the some valves should be on or off. So something like that. So these are the basically different key components of this particular system. There is one more work that you can see, Sustainable Communication Journal. That is also very good journal in 2020. You can find this problem that how to detect this deficiency of the nutrients in the soil and adding the fertilizers at appropriate quantity during the lack of nutrients. So it is basically having a soil sensor, which is this measuring this, not soil sensor, you can say that it is basically NPK sensor, which can measure the concentrations of nitrogen, phosphorus and potassium. So then, what is the output? That IoT-based system is basically intimates the farmers about the fertilizer at the right time automatically through the SMS. And then there is a basically in the background, these methods can be implemented for softwares and all this. So there is a system which is talking about, which is having these different sensors, okay, to sense this NPK sensor value from the agricultural field, and then analysis of the soil nutrients at the cloud by using some some data analytics tool, and then generating this SMS alert system, so which is basically from the cloud itself, so Wi-Fi or Raspberry Pi. It is basically done from the Raspberry Pi to create the alerts to the farmers. There are other applications. So it is talking about the different network layer where these applications to be implemented. So you can see that IoT functional architecture area is basically here. The sensors is directly connected to the Raspberry Pi, and you have some analytics results to see. Now, edge computing is now booming up. So people are talking about this edge computing because of this reason, that if all the data, whatever collected by this Raspberry sensor and Raspberry Pi is going to be sent to the cloud, then there will be a lot of network congestion because a lot of data are being sensed. Because nowadays, means IoT devices are increasing. So that's why if some of the part of the task which is going to be run in the cloud can be run on the edge device, like in the Raspberry Pi itself, then we can have this edge computing, and then this particular results can be sent to the cloud only. So this kind of structure is nowadays people are thinking of. And then there is an example of another improvement, another work that is talking about this plant disease. As I mentioned, it is basically taking care of this different plant disease data set, which is basically image data set, and they are applying this AI-based techniques. This particular tool they are proposing in this paper in IoT journal. This is very good journal, top journal, where they're talking about this Base Care AI tool. So where this plant growth management system they have built up, along with this different things like there is a TensorFlow as an API they have used for this ML and DL based techniques to apply on the data, and clouds for cloud computing for storing the data and training the data in that cloud, and then mobile application for getting this results. so that when the image is captured by this mobile, it can do the classification of the vegetable, like which vegetable it is. There is some trained data already based on the data. The trained model is there, and what kind of plant disease it is having, and the insect pest classification also, that what kind of insect is attacking this particular plant. So these kind of services are available by this system. There is another, so they basically, in the same paper, they have basically talked about different types of plants. You can see different types of plants, their images, and from these images, they are basically having this AI and you can say the DL-based approaches, the DL-based techniques to identify the diseases and the plants, means leaf, based on the leaf, what plant it is, what crop it is, so that they classify. You can see the paste data set also. They have the paste data set, and they have used this paste data set for different type of uh, plants like rice leaf roller, or rice leaf, this hopper, leaf hopper. So these are different insects, you can say. Corn also, they have done this. And then the last one is this IoT and DA in agriculture. So together, this is also IIT journal in 2022. So they talk about the different applications, different kinds of that we have already discussed, are integrated together to build up this IoT-based system. Okay, I have to finish quickly. We are on time. So basically, IoT ecosystem is talking about this different kind of system development, which is integrating this IoT, this cloud IoT platform, data analytics, where this ML and AI based techniques are used, and there's also app development like mobile app or web app development, along with the hardwares. Those are inherently required for this sensing the crop field or area. So I think I'll skip this part, this literature part, and I'll come to directly to this hydroponic system, which is very new, and we are working on this in our lab also. So this is the hydroponic system. There are two different systems. One is this vertical one, that is aeroponics also. This is sometimes called aeroponics. So there are different cups where these plants are basically hold, and there is no soil is used. There is a coco pit that in which this is getting the support, and also getting the water through that. And there is a hydroponic system, which is basically horizontal setup. You can see the water is there, water pump, it is pumping the water to this channel, through this pipe, and these cups are basically holding each and every plant. So one plant in one cup. Okay, so there are two different kind of systems available in our lab. We have set up this in our residence and some place, and then there are basically different kinds of plants we are growing there, and then monitoring the data through that. So this is known as the hydroponic system, and where this is basically no soil is being used, and these nutrients in the solution in the water are being monitored, and based on that we control the system. So basically, nutrient film technique, this is the most popular one. This is efficient of use of water and ability to provide the optimal oxygenation. So these are very important for hydroponic setup. So I think I'll skip this part. So there is a particular system developed by our students, my students here, by using this, again, this node MCU ESP8266 and different sensors. By using these different sensors, they are basically monitoring. I think this is the node, this one particular MCU. So this is a ESP8266. And there are different sensors that we have used, that is DHT11 sensor, which is basically collecting the data for the temperature and humidity of the ambience, and also for the water. And then we have this a particular ultrasonic sensor. Ultrasonic sensor is used for this means to distance measurement. For some reason, we need to measure this also for ultrasonic sensors, for measuring this water level actually. So for what is the water level in the tank, so that we can fill the tank automatically. So this sensor is used. And like this, we have developed a system, and okay, sorry. So I think I have to skip this part, but screen is not moving. Yeah. So the system was like this. So it has this kind of extension board where we have used this setup, fix the sensors. You can see the schematic diagram here, and then this block diagram is showing that how this setup. So this is one node, so this is a n node, this is one particular node, such that like this we can add 5 6 such nodes and then create a network connection through this gateway. And we have used this LoRaWAN net gateway to connect to the internet and then get the data stored in the cloud. ThinkSpeak we have used there, and then using the dashboard, user dashboard, we can access the data and see the monitor the plant growth. So I'm not going into detail of this. So LoRaWAN has been used here for as a network communication for connecting the data, sending the data to the cloud. Okay. So last part, just let me check this message first. Okay. No problem, sir. You may continue. Okay. No, I'll finish soon. Which type of plant are you using in the hydroponic system? Okay. So we have used this spinach, and we have used spinach and then basil, and one more strawberry we tried also. Yes, but it did not success strawberry. But spinach and coriander. Okay, coriander, it worked very nicely. We use that in the hydroponic system. Coriander and spinach and basil. All three worked very fine. We have monitored the data. We have collected the data also. We just for some season, one last year and this year also. Okay, so just moving to just giving a glimpse of machine learning, because this workshop or this seminar is on deep learning. So you should know about this also, related to smart agriculture, that we are going to use machine learning tools right nowadays. Because of this data we are collecting, gathering from that data, we want to learn something, and we want to find our model. We want to find out our algorithm. So this model development is that is developed model from the data set that we collected. We need this data model to be implemented in an edge device. So now edge device, as I mentioned in the edge computing when we are discussing, so we are not going to send the data to the cloud. We are going to do it in the Arduino board or in the MCU, that node MCU, whatever be it is, like ESP32 or ESP8266 or Arduino or Raspberry Pi. So these are all having limited capacity of processing as well as memory. So whereas these machine learning models, if you are talking about this deep learning models, so one particular model may be huge, which cannot be implemented on this edge device. So there is a challenge here, that how we can make this tiny ML applications, small ML applications, small ML model, so that we can implement this in our edge device, which are having limited resources, like Raspberry Pi or this one. So this topic, a tiny ML, is talking about this emerging area, this very emerging area nowadays, where ultra large powerful ML models can be converted into executable on embedded system. So we have embedded system, we have a ML model, which is for maybe GPU to run. We need GPU to run that particular model. So now we have to find out the representative tiny ML model, ML, which can be run on the embedded system or maybe our microcontroller. So there is basically a new development that has come from the TensorFlow again. So TensorFlow Lite has come, so which is having this all these packages and all this. So they're basically training this data distillation, quantization, encoding, and compilation. All this they can do on this small microcontroller. So this TensorFlow Lite, there is some packages also. Basically, you can use directly the TensorFlow Lite and their functionalities to get this done on the edge devices. So you have a cloud ML. For this, you need TPU, DPU, GPU, FPGA, and CPU. Whereas in case of edge device, you need SoC. SoC means in the mobile you want to do. Maybe even further smaller. So edge devices, we're talking about this mobile devices, but now we are talking about tiny. Tiny means very small. Like it is basically you can say that microcontroller unit, like your this Arduino or Raspberry Pi. Anyway, so there are different applications we can build up on this. And then these applications, basically tiny ML applications for different agricultural sectors. We can think of this. There is another sector also, tiny ML being used, not only just for agriculture. That is just one example, which is telling in that plant disease classification by using this TensorFlow Lite on Android phone. Okay, so TensorFlow Lite, because this data set, when it is being used for the plant data set, the classification problem is challenging, and then this the trained model is also heavy. So this TensorFlow Lite helps us to do it in the Android phone also. So that is an application of TinyML. So you can see the different schematic view of this TinyML and its phases. So it has raw data and features and process data, and then learning algorithm, which is as usual we do for this computer in the computer, and then get a model. Up to this is fine. And then compressed model, we want to find out. This is a model compression we have to do, and then model deployment for field testing. So this is basically the application phase of this TinyML. So TensorFlow Lite gives us this thing. So train the model, convert the model. So this is there is a function actually which is called this convert TensorFlow, TensorFlow Lite dot convert, something like that. So you can convert the particular model that you have already trained for target hardware that you are going to use. So it may be this microcontroller, particular microcontroller Arduino base, or maybe your mobile phone, which is having little more than this microcontroller, or maybe Linux, embedded Linux like your GNU Linux or Raspberry Pi. So this you can optimize this model particularly, and then deploy that model and run the model in this particular low-end processors or low-end controllers. So that is our target. So that is the next target. So this edge computing with TinyML means that we have IoT devices in different applications areas, and we have sensors data, and particularly we want to do this edge computing. So in conclusion, I want to conclude now. I have some questions, I guess. Let's see. Which type of plant? Okay, this is I have seen. For hydroponic systems, let me answer these questions. For hydroponic systems, coriander, basil, what was the third one? Okay, so basil and coriander and spinach. Yes, spinach. Yes, right. Okay. Okay, you have already answered. Thank you. So this is the conclusion that we have different inputs data to be collected from the crop or the agricultural land using several sensors like crop data. You may have environmental data, you may need soil data. Crop standards are also there for different government rules and regulations from the agricultural ministry. And weather forecast also we need to take as an input. Maybe sometimes best practices like our uh, ancestors have used some practice, so that is the best one. We can borrow that one. So in our, not only just taking this IoT for replacing our everything, and then government policy also has the input, and then market demand. Obviously there is a demand for agricultural output. And the processing means that we have to prepare the land. So land preparation, sieving, that how to do all these automations. All these tasks need to be automated. So by using this IoT and your smart agricultural techniques. So sieving the seeds, and then irrigation, fertilization, and then pesticides throwing, and also harvesting. Okay. And the output is basically to increase the quantity, quality, and control everything, quantity and quality of the product of the crop that we are getting as a end product. Yeah, we have to increase our economy also. We have to improve our economical condition, and future prediction is possible for the future plant growing, and then update the standards and policies and best practices as well. So this is a giving a feedback to these particular things. Okay, so that's why this is very fascinating field nowadays. You can, if you are getting interest, you can start working on this. These are the references I have used from some of these papers, some of the materials. So this is our institute. It is IIT Roorkee, and it's basically became IIT in 2001 only. Although it is it is the oldest, first engineering college that was established in 1847. This is my lab website. You can visit this website, Coda Lab. I named this lab as Computing and Design Automation Laboratory because my main focus is on this microfluidic chip design. And I also work on nowadays on chip design for this IoT for smart agriculture. And I am also associated with this joint faculty in the Center of Excellence in the Disaster Management and Mitigation and Management. So there I have some students who are working on this application of AI and machine learning, or information and communication technology for disaster risk reduction. So this is the some of the photos of my lab, you can see. And if you are interested to do internship in our lab, in my lab, so you can apply for this Park and SRFP. This is the internship opportunities. And if you want to apply for this PhD, so this is the old one, the last year's advertisement. Yeah, for this year already we have conducted the interview. So for the next time, you can look into the website there. And then if you have any question, directly you can write to me in this email IDs. You can visit my website, which is not very updated frequently. So that's all from my side. Thank you. I took 10 minutes extra, I guess. Yeah.
Thank you so much, sir, for your expertise and the knowledge that you imparted in us. Each and every one of us are very grateful. Sir, apart from this, I also request you to kindly share the slides with us for our reference.
Yeah, sure. I will. I'll share.
Okay, sir. Thank you so much, sir, once again for the session.
Yeah. Thank you very much. Yeah. Okay. Can I leave now?
Okay, okay, sir.
Yeah. Okay. Thank you. Yeah,
Thank you,
Akshay.
sir.
Yeah, please
Yes, sir.
continue.
Thank you, sir.
I
Thank
have
you,
to
sir,
go.
for this nice
Yeah.
presentation, sir.
Yeah. Yeah.
Hopes we will meet soon, sir, in the
Yes, yes,
campus, sir.
yes, yes, sure. You please continue. I took your 10 minutes time. You will
No,
be
no,
late.
no, sir. It's not the
Yeah.
issue. Thank you so much, sir, for
I
this
have to
nice
leave because
presentation.
I have another appointment here to
Okay,
IIT.
sir. Okay, sir.
So I'll listen later on. Yeah. Thank
Thank you,
you.
sir.
Thank
Okay,
you.
sir.
All
Thank
the
you.
best. Bye.
Bye, sir.
So we have our next speaker with us. I welcome you, sir, Dr. Akshay Pandey, sir, to the 18th day of Deep Learning Summer School. Dr. Akshay Pandey is an assistant professor in the computer science department at IIITDM Jabalpur with expertise in UAV-based remote sensing and geospatial data processing. He earned his PhD from IIT Roorkee, focusing on deep learning techniques for agricultural monitoring. His work spans UAV assembly, multispectral imaging, GPS integration, and web GIS systems. Dr. Pandey is also a founding member of Raven Eye Geospatial, a startup incubated at IIT Roorkee, and a collaborator in the Endangered Wooden Architecture program funded by Oxford Brookes University. His research targets real world challenges in precision agriculture through advanced AI and geospatial analysis. Thank you so much, sir, for joining us today. I now request you to kindly take over the session.
Thank you, Sunena, for this warm introduction in this warm environment. And I think most of the part have you seen in the previous presentation related to the AI integration with IoT and for the data set for smart farming purposes. So in this presentation, just give me 1 second. I am just sharing my slides. I hope you are getting the first slide of my presentation. All?
Yes, sir, it is visible.
Okay. So, like in as my expertise in different GIS and GPS techniques also. So from the my PhD experience, and after that I joined as an assistant professor. Then I found one like a name of agriculture, UAV, and farming. So the UAV, we can say it's a game changer in smart farming. So with this, what type of smart farming is requested, and what we are doing actually, our farmers, our policymakers are doing in the nowadays. So in this presentation, we will explore the integration of unmanned aerial vehicle or drones, and how AI in the field of smart farming will help. So we will examine how UAV enable high resolution time series monitoring and water stress, soil health monitoring, pest infestation. So this with the help of AI and these parameters in the form of data play a pivotal role in processing and interpreting the data using the advanced algorithms such as deep learning, image segmentation, predictive analytics. So, with the help of togetherness of UAV and AI in the form of backbone of data-driven agriculture, enabling precision intervention for optimizing inputs uses like fertilizers and irrigation. So, starting with this, yes. So I can say when we are combining all the IoT, UAV, AI, software, hardware, data is equals to smart farming. So smart farming is the application of advanced technologies like AI, Internet of Things, drone, GPS, sensors, and other data analytics to enhance the efficiency, productivity, and sustainability of agriculture practices. So why smart farming? So the answer is smart farming uses a real-time data or near real-time data, we can say that, and automated system to optimize crop production, reduce the resources uses like water, fertilizer, pesticides, and enable precise decision making, thereby transforming traditional agriculture. So in this, come into the basic scenario of our Indian agriculture. So as of the 2023 or 4 agriculture year, the India achieved the record food grain production, 332.3 million tons. So it's a surpass from the previous year. As per the reports from the Agriculture Ministry, the horticulture production decreases is approximately 0.91% compared to the 2022 and 23. So this noticeable decline in the net irrigated area dropping from 77.9 million hectares in 2021-2022 to 69.48 million hectares in 2023. So it's like a decline. And also when we are talking about the GDP, so Indian agriculture share is also decreased in this 2023 and 24 by 1% something. So these kind of changes may be done some some of the part of our agriculture land, some traditional techniques. So these are the major challenges of traditional farming practices. So we have a low productivity. So the reason is that due to manual tools we are using, poor seed quality and lack of mechanization, soil degradation, water mismanagement, lack of technology use, minimal use of modern techniques, sensors, or data analytics, pest and disease vulnerability, post harvest losses, market dependency also. So these are the like challenges which we are having in the agriculture now. So with this, the traditional agriculture faces like different low productivity, resources, insufficient resources use, crop monitoring, poor pest control, precision agriculture, or using UAV addresses. These by enabling near real-time monitoring of crop health, soil condition assessment, and irrigation status. So, as we can say that the UAV help in early detection of disease also and allow timely intervention in the agriculture. So, as UAV, all of you know, it will provide a high resolution imagery and will support for better decision making and farm planning. So with this, we can go with the step by step for production, for enhancement of horticulture production and all. So here you can see that how the AI will using in agriculture, how our policymaker, researcher, farmers, so like they are using the automated farming activities, managing crop quality, identification of pest and disease outbreak, and monitoring biotic abiotic factors and stress from the crop. Then AI-enabled drone is in insect and pesticide spray. So these are the like how the different hardware, software, AI techniques, the algorithm are helping in agriculture. So when we are coming to as we discussed in the first slide, we have the hardware, software, IoT device, drone, and data is equals to a smart farming. So here are some components are visible. So in the first, like we have a one spectroradiometer, then we are having a MicaSense red edge camera with GPS. So we are getting a multispectral image, means we are getting a 5-band images of agriculture, which will help to calculate the vegetation index. Satellite, freely available satellite, the Landsat 8, Sentinel-2. And in this, figure number 5, you can see there is a one drone having a RGB camera. In figure number 6, there is another drone having a multispectral camera. These are the hardware which will used for agriculture. And now, as this is if you are supposed to do processing in real time on the UAV, means you are on board processing, as most of the peoples are continuously, as sir is also discussed in the previous, the edge AI is very popular nowadays. Why? Just because of this, like we are having a lightweighted AI ML models. So if we have to process the near real-time data using the UAV images, so this kind of Jetson Nano will help. So the NVIDIA Jetson Nano is very tiny, as like one very grams weight having, and power efficient also. So it's not a simple sensor, like we can use a full Linux operating system within this NVIDIA Jetson. And also along with the operating system, along with the GPU, which will help to process the image in real time. So to turn it into the IoT device, you have to install the lightweight software like MQTT and the sensors, AI-based alert, the Wi-Fi sensor, Ethernet sensor. So that is possible with the help of this NVIDIA Jetson. So this is for the, and these are the some softwares which will helpful for data processing and make the fruitful decisions by using the Pix4D Mapper, AGI Soft Photo Scan, Bentley Reality Capture, 3D Zypher, Survey, Mensi, Autodesk, Photomod, Drone Mapper, WebODM. These are the softwares which will help to process the image. And as we come with the devices like hardware, so we are having the robots, drones, sensors, thermostat, GPS tracking. So these are the like basic device. So here we are discussing the UAV. So in this here you can see these are the basic like classical example of UAV. So UAV, why the UAV is very cost effective and nowadays time efficient and high resolution. Their ability to get the real time data with high spatial and as well as temporal resolution. So UAVs are cutting edge technology. So with this, from when we are in the old days, so we are having this kind of classical example of UAV, how we are getting the aerial images from our agriculture using the parachute, using the some mounted device on the air, some aeroplane. But right now we are having a compact or small devices like a UAV. So UAV is an aircraft. You all know about this. Operated without onboard pilot. There is no pilot required on board, and offering flexibility and safety also. So as in 2012, the US government accountability office survey found that 75 plus countries have adopted drones for data acquisition in the area that they are in the remote or very difficult to collect the data. So that is possible with the UAV. So the UAVs are utilized in diverse applications such as payload delivery, traffic monitoring, surveillance, working in hazard, and ensure the safety also. So these are the kind of UAV that we are using nowadays. So when we are talking, we just give the brief. So we are having a different types of UAV. We are having a multi-rotor. So multi-rotor means it will equipped with the multiple rotors. These UAVs are commonly used with small cameras for precise and vertical takeoff. Okay, so and another one is fixed wing. So in fixed wing, it's like a traditional airplane. So using wings for lift and ideal for long lasting flight, or we have a long endurance required, so that we have to use the fixed wing. And we are also having a single rotor helicopter. So whether it is multi-rotor for precision, because the fixed wing are for coverage, for single rotor for stability. So multi-rotor is useful for capturing the data in the form of agriculture or any other objective. So this is a basic working principle of multi-rotor quadcopter. So a quadcopter features 4 propellers positioned at the corner of its frame. Each propeller's speed and direction are independently controlled by the balance and movement. Uh, in traditional quadcopter, the rotors are evenly spaced, with one pair rotating clockwise and other pair is counterclockwise to maintain the balance. To hover, all rotor must run at high speed, and by adjusting their speeds, the drone can move forward, backward, and side by side. So this is the basic working principle of quadcopter. These are the UAVs which are available in the market. So different like Phantom 4 Pro, Mavic, these are the DJI drone. These are the Parrot manufactured drone, Anfi, Beep, and the Autel, Skydio, Unique, Trimble, EB. So the entire system, here you can see there is a one remotely piloted here, there is a one kit, and there is a one UAV. So this RPAS, so this entire system is known as unmanned aerial system or remotely piloted aircraft system. So these are the components of UAV or UAS. So the first is unmanned aerial vehicle, then the communication data link. So with the help of data link, you are enabling the real-time data transmission of the UAV and the ground control station. Then the third one is ground control station, the operator base for controlling and monitoring the UAV flights and mission parameters. So these, the key effective using the US photogrammetry and remote sensing. So the mission planning and real-time mission management. These are the classifications. So UAS is categorized as rotorcraft, aeroplane, and hybrid that we already discussed. And these are the based on the size, the classification of unmanned aerial vehicle system. So nano drone, micro drone, small, medium, and large. So they are basically categorized on the basis of the total payload capacity and the total weight. So these are the classifications. So here you can see this. Different UAV systems are, so nano is 250 grams less than. These are the basic anatomy of the quadcopter. These are the very important parts for any drone. If you are going to assemble any drones which using the different parts. So with this, you can also assemble the drone. And these are the drone rules that you have to follow to fly the drone in the for agriculture or research and purposes. So these are the what you need to do and what is not required for which kind of drone. So suppose we have to collect the data. So when the pilot or autonomous system gives the drone to a command, it means we are going with the manual flight planning or the automatic flight planning, it depends. The flight controller sends the flight controller, it means your ground, GCD, ground control station, sends the signal to the motors to spin the propellers. And the speed and directions of the motors and propellers are adjusted to achieve the desired moment. The sensor provide data, the flight control, which uses to stabilize the drone in the air and adjust the movements. So the drone can be controlled manually using the remote control or autonomous also. So when you are able to capture the drone imagery, so here you can see the upper part is UAV image and the lower part is satellite image. So you can see the comparison, the how we are getting the exact or high resolution image in UAV as compared to the satellite. So various sensor which is required to capture the images. So UAV equipped with the lightweight RGB cameras, we are having RGB cameras have become a standard tools in remote sensing and photogrammetry, and advances also being made in customizing UAV payloads with a specialized sensor. So if we are using the multispectral sensors, so multispectral sensor supports application like crop monitoring, forest health, and leak detection. If we have to go with the thermal sensor, so thermal sensor they will help to temperature based analysis for predictive maintenance. And if we will go with the hyperspectral sensor, so the hyperspectral sensor capture the image across of hundreds of spectral bands and used in advanced earth science application uh, involving land, water, and atmospheric studies. So these are the different sensors that we can board on our UAV for the data collection related to the agriculture. So as UAV technology is continuously to evolve, and they are becoming a central to a broader transformation in agriculture. So one that the parallels the historic green revolution, but it is driven by digital and intelligent system. So we are now entering the era of technology revolution where smart agriculture or farming integrates sensor-equipped UAV with AI, data analytics, and precision farming techniques to address the 21st century challenges. So the challenges are from doubling the agriculture productivity by 2050, to reduce the food wastage and post-harvest losses by up to 50%, as highlighted by the FAO. And the smart farmings offer a strategic leap forward towards sustainability. So this transition from a green revolution to technology driven revolution is not just about the producing more, it's about producing intelligently, efficiently, and responsibly. So with this, so the drone integration for precision agriculture. So when we are equipped with the RGB camera to drone to capture the high resolution aerial images from the field, then these images are processed into vegetation indices or thermal maps or vegetation map. So by covering the large area quickly, drone provide a comprehensive macro level and perspective of crop performance. Spatial variability insights enable agronomists to plan targeted intervention like variable rate spraying or precision irrigation. So the overall drone-based aerial mapping or sensing empowers the farmer to optimize inputs, boost yields, and conserve resources. So with the continuation, so when we are talking about the smart farming, so the first is we need to identify in the agriculture land what type of crop and which type of crop is there. We are having a rice, we are having a sugarcane, we are having a wheat or different crops. So the accurate crop identification form the baseline of a smart farming decision. That is a baseline. So with this crop identification, we can monitor the health, growth stages, spatial distribution across the fields. So we can say that if we are able to identify the crop, then this input will help in all the monitoring of the crop health, growth stages. So that can be done. So with this identification, targeted like irrigation, fertilization, or because the without knowing what and where the crops are, precision agriculture or smart farming cannot be possible. So for this, we developed a one CDCNN architecture for intelligent system for crop identification and classification using UAV RGB images. So it will start from the crop level where sensor monitor parameters like soil temperature, moisture, and plant health. This sensor data is transmitted through a platform like UAV and processed by a software system. Then collected data is then analyzed using AI algorithm to extract insight and generate smart decision. So these decisions are implemented through automated or human acquisition system So in this, the first step is data collection. So for data collection, we have to decide the area where we have to collect the data, means our area of interest. So in this, according to our area of interest, we have to plan the flight planning with using the different software to collect the data. So this is a flight planning steps, and how we are going to collect the data using different flight planning missions. So there is a one, like we are having a different type of hexagon or pentagon, or we are having a continuous area of interest is also possible with this. There is another data collection flight planning. So here you can see we are having a multiple lines to collect the data in the form of field, and this is another data collection. So when we are like going to manual data collection or automatic data collection, so these three figures are which you have which I have shown to you. These are the based on the automatic data collection. You just need to mark your total area of interest, and UAV will go from your home point and it will collect the data. So after the data collection, you are able to get this type of data. So this is a number of images for that field. So these are the grayscale images for multispectral data set we are having. So and if you are using the RGB camera, so this type of images you are getting for RGB sensors. This is a broader of multispectral data image, and this is a RGB data image which is captured by the UAV. And when you are having this type of multiple images, so then you need to develop a one mosaic images. So that is called the orthophoto. So after this, all the images, you are able to generate this ortho image or mosaic image to your agriculture health analysis or what you want per your objective. So need of this as the global population towards the estimated 9.6 billion by the year of 2050. So the demand for food is expected to rise dramatically. So this pressing the challenge call for transformative shift in how we are approaching the agriculture rather than expanding farmland, which could harm ecosystem and strain natural resources. So this is where smart farming became essential. Like we have to do in anyhow, we have to apply the smart farming for precision agriculture. So at the heart of the precision agriculture, like the first step is crop identification and then classify the crops. So the crop identification, therefore, is not just a technical step, it's a foundational requirement of smart farming. And so in this continuation, the benefits of UAV based, so the unmanned aerial vehicle have revolutionized the crop identification by offering a high resolution near real time imagery that capture even different like challenging condition in different vegetation indexes. So it is also not like a satellite data, it's a very fine resolution data set, and their ability to cover a larger area quickly improves monitoring efficiency. With multispectral and other sensor, UAV can detect the crop stress early. So UAV-based crop identification enhances precision, reduce input waste, and support data-driven decision-making in agriculture. And in the entire system, there is no human intervention is required. So UAVs are equipped with that, as we discussed in the previous slide. We are having a multiple, like a multispectral, hyperspectral thermal sensor. So in multispectral, we are having a 3 to 10 bands, and hyperspectral, we are having 100 of bands. And in RGB, we are having only 3 band, red, green, and blue. So when we are having this kind of data, and with the help of this RGB, if we are able to identify the crop, then it will help to reduce the time and as well as the cost also. So on the basis of RGB data, So most of the studies using the RGB data. But recently, most UAV-based crop identification limited to binary classification, means they are just finding the crop and non-crop region. So, in fact, when our research was initiated, so no significant multi-class crop classification is there. So at that time, the machine learning approaches required separate manual feature extraction layer. So in the past year or two, the very few studies have worked for the binary classification or weed and non-weed or crop and non-crop region they are able to identify. This evolving landscape underline the growing relevance and timeless approaches, especially in context of the near real time. So different CNN, as you all know about the convolution neural network, can be trained using different architecture, learning mechanisms, each designed to improve performance and overcome certain limitations. So the most form of is plain learning, where layers are stacked sequentially. Each layer transforms the input and pass to the next layer. However, as networks are deepen and plain, uh, uh, the so this type of architecture often suffer from the vanishing gradient problems, which hampers the training. To address this, residual learning was introduced. So most famously, you know about the ResNet. So where escape connection allowed to model to learn identity mapping and gradient to flow more easily through the networks. So this helps in training much deeper models effectively. So building further on this idea, dense learning uh, as seen in DenseNet. So it will help to connect each layer to every other layer in feed-forward network. So this is not only strengthen the feature propagation, but also encourage the feature reuse and significantly reduce the number of parameters. So together, these learning mechanisms represent a progression towards more efficient and deeper networks capable of learning their richer representation from image data. So the RGB, so first we have to collect the data. So this is a flight planning steps. So in our for this research, we used one drone as Phantom 4 Pro V2 UAV version, which comes equipped with 20 megapixel digital RGB camera, allowing us to capture high resolution UAV imagery. Before each flight, we carried out the careful flight planning, which is crucial step in ensuring consistent and accurate data acquisition. So this planning involved the fixing the flight path, which is present in the above image, and to cover the study area systematically. So determining the flying height to balance the resolution with coverage and setting the camera angle, typically nadir, for uniform ground sampling. Additionally, we configured both side overlap and front overlap, usually above 70% and 80% front overlap. So to ensure sufficient redundancy for image stitching and 3D reconstruction during post-processing, this structured approach to data collection laid a solid foundation for reliable crop classification or identification results. So these are the images. These are the demo images of 5 types of crop: rice, sugarcane, wheat, beans, and there is a one grass. So 5 types of crops. I collected this data from different region of India, like Madhya Pradesh, Chhattisgarh, Punjab, Haryana, Uttarakhand. So these are the study area map. So in this, we follow this sequence. So first we have to the input image for the data collection. Uh, After capturing the high resolution images using the UAV, the next critical step is our pipeline was to segment the crop and non-crop region, which is very important to create a structured and labeled data set for training our classification model. So the original raw images was very high resolution, is having a 5472 into 3648 pixels in a single image. So then we have to identify the crop area. So the working directly with the such large area is computationally expensive, as you know that it's a very high resolution. So we applied a candidate region extraction step in this algorithm. So essentially, like what we are doing, we are isolating the relevant crop patches from using the ISRI RJS software. And this was followed by resizing the extracted regions using the Python script and making it suitable for CNN processing. So this segmentation and pre-processing phase ensured that our data set was clean, balanced, and computationally efficient for training deep learning models. So in the continuation, when the candidate crop region are extracted, then we are fed this candidate crop region to input to the CNN, which is core of our classification model. So the CNN operate through four main stages, as you know that: the convolution, max pooling, flattening, and classification. So this in the convolution layer, we use a set of filters that slide over the input images to extract the key features. So these filters detect patterns such as edges, textures, or shape by performing CNN operations. So convolution operations producing what we call the convolved feature map. So to reduce the size of these maps and focus only the most important information, we apply max pooling. Okay, so this operation scan all small region of the feature map and select only the maximum value, effectively downsampling the data and reducing the computational load. After this pooling layer, we flatten the output, transforming the 2D data into 1D vector data. And this vector data is passed into the ANN, which assign the weights and perform the final classification. So during training, if the model misclassifies the region, the ANN adjusts the weight to improve the performance and ultimately enhancing the accuracy of the system over time. So here you can see the dense CDCNN architecture. So let's now take a closer. So in dense block architecture used in this crop identification model, which is adapted from the architecture as shown in this figure A. Here you can see the figure A. The dense block is designed such that each layer receive the output from all preceding layers. This is represented by the feature map concatenation. So in this, you can see this R0, R1, R2, RL minus 1. Each layer learns new feature based on the composite function FL. So this composite function performs batch normalization and convolution. So the batch normalization helped by standardizing the pixel intensity ranges from 0 to 255 to a normalized 0 to 1 scale. And simplifying the computation and stabilize the learning process, the convolution part, as discussed earlier, extract the meaningful spatial features from the input. Now to make the network efficient and avoid irrelevant of redundant outputs, an activation function is applied after each convolution. So this traditional, most of the authors used ReLU and SeLU, which so as all you know about the ReLU and SeLU. Here we use the customize activation function SLReLU, which will help to find the more accurate result using the. So here you can see in the figure C, this is a ReLU activation function. So this is the overall conjugated dense CNN architecture. So in this figure, you can see there are two dense block, the overall for class two dense block for crop classification connected by intermediate conversion block. So So in each dense block employs a feature intermediate concatenation mechanism, and meaning the inputs and output of all previous layer, as we discussed in the previous slide. So this promote the efficient feature reuse and improve the gradient flow. So after dense block 1, the conversion block applies a max pooling operation. Okay. So with this max pooling operation, reduce the spatial dimension of the feature map. So in this, after the feature maps, the speed will of our training process will increase without the significant information loss. So the output is then passed to the dense block 2. So when we are having this reduced or significant output, then we passed it to the dense block 2. And in dense block 2, subsequently, we also use the SL-ReLU activation function once again, which will help to suppress the irrelevant activation and refine the feature quality. So finally, the network applies the flattening operation and to convert the feature maps 1D vector, which is passed through a softmax layer. The softmax function assign probability score to each crop classes, and the image is classified into a particular class which having the highest probability. So this is a layered structure enable precise and robust architecture for crop classification. So in our studies, we focused on 5 different crops. For each class, we use the data set of 2000 UAV based images, and each with a standardized pixel of 342 cross 342. To ensure the robustness of this model in training and evaluation, we randomly selected 1400 images per classes for training, while 600 images for uh, testing purpose. So this 70-30 ratio split help us to assess the model generalization capability on unseen data, and to comprehensively evaluate the performance of this proposed conjugated dense convolution neural network model, we computed the separate several standard classification matrices like sensitivity, specificity, precision, recall, and F1 score, false positive, and more. So these matrices provide a multi-phased view of the model's strength and limitations. So additionally, what we have done, we generated a confusion matrix which visually illustrate the how accurately model is predicted each crop in each class and where the errors are coming. So they'll help to validate the effectiveness of our approach in distinguishing between the different crop types using UAV RGB imagery. So this is a confusion matrix results. So I compared CT-CNN architecture with all the standard and machine learning and deep learning architecture. So we compared with the random forest 200, SIFT, SVM, AlexNet, VGG16, 19, and ResNet 50, dense CNN, and CT-CNN, which is our model. So in this confusion matrix, our data set is 600 images for per class. So the confusion matrix offer a clear visual representation of how well we are getting the results. So you can see in this diagonal, the actual classification is done, and off diagonally we are seeing the misclassification. So by analyzing these misclassification, we can understand there are model where the model struggle. For instance, if two visually similar crops are frequently confused. So the comparing matrices across method allow us to identify which architecture or learning mechanism yield the most precise and reliable classification result by using the different machine learning and deep learning and dense learning model. So in this, we comparatively studies about the class-wise comparison. So the standard machine learning architecture, standard CNN architecture, and dense CNN architecture. So in this, first we have class-wise comparison. So you can see all the results are in bold black. So first we have to go with the rice, sugarcane, wheat, beans, and grass. And then we calculated the accuracy, sensitivity, specificity, F1 score, FPR, and total training time. So in the results, so uh, the evaluation based on the best performing values you can see in the CDCN architecture. So this confirms that the efficacy of feature reuse and deeper gradient flow enabled the dense connectivity. So that will help to making it most effective model for UAV based multi-class crop identification and classification for our experiment. So in this, we also compared our model on the epoch base with different CNN and our other architecture. So the figure you can see here in this epoch based comparison. So the figure at the top, the slide illustrate the training process of various CNN architecture, including the LXNet, VGG 16, 19, and ResNet 50. So in the figure you can see clearly, while all models eventually stabilize with rolling iteration, the training speed of LXNet and VGG networks is uh, relatively slower as compared to our model. More importantly, one stability is reached, significant fluctuation is training accuracy are evident that most architecture expecting for CDCNN. So this stability reflects the robustness and the efficiency of our model during learning. So in the other hand, you can see we also compared our CDCNN architecture with one dense block, two dense block, and the three dense block. So you can see clearly we are having a good result in CDCNN architecture while we are maintaining the reduced time in CDCNN architecture. Then we also compared our CDCNN module with the activation function, ReLU, SELU, and SL-ReLU. So you can see here, we are getting a good result in SL-ReLU architecture activation function. And then in the part of this study, the further investigated the impact of different activation function, the performance of our model CDCNN. Specifically, we compared the training and testing outcomes using SELU and ReLU and our custom designed SL-ReLU activation function. So as shown in the this evaluation indices, the testing accuracy is high when using SL-ReLU, indicating its superior generalization capability. So moreover, the training process with SL-ReLU is noticeably more stable, showing fewer fluctuation compared to the ReLU and SELU. So this stability play a crucial role in achieving the consistent convergence, especially in deep learning architecture like CDCNN. So these results, SL-ReLU, as it balance the strength of soft sign, ReLU, and logarithmic function, handling negative and standard and high pixel value respectively. The efficacy evaluation matrices including accuracy, precision, F1 score, recall, and confirm that the SL-ReLU provide the most reliable and accurate crop classification results. So now come to the conclusion. So this study addresses the challenges of accurate crop identification and classification by leveraging the high resolution UAV imagery collected from different various crop fields. And here you can see the novel deep learning architecture named as a conjugated dense convolution neural network has been developed featuring a custom designed activation function called SL-ReLU. So this architecture not only achieves the higher classification accuracy, but also demonstrate faster training convergence compared to the standard CNN model. So the most importantly, it allows us to accurately identify multiple crop type using a single unified tool. Such a tool holds great promises for policymakers, agriculture planners, and farmers. So, offering data driven insights that can enhance decision making, emphasize the resource use, and support for future of the smart farming. So, in this presentation, I will also show you a one web portal for the UAV image processing. So what you can do from this, if you are having the UAV data set, you can directly process your UAV data set without having a more GPU and all. You just need a one internet access, and you can select all your UAV images, and the result will generate it very fast and efficient. So we developed different API based and deep learning based web GIS model for this multispectral RGB image processing of UAV. So here you can see that first we have to create the project, and then we need to upload the images. After the data uploading, we are able to generate the orthophoto as we discussed. So this is the orthophoto generated from different collected images. And if we want to go with the smart farming, so we need to calculate the indexes. So there is no need to any other software. You can directly calculate the different indexes using this WebGIS portal. So this is a complete presentation from my side. So if you have any question, please feel free to ask. Yes, anyone can ask the questions. Yes, Sangeeta, you can ask. You can write in the message box. How research I can use the WebGIS portal. So if you want to use this WebGIS portal, so what you have to do, you have to write a mail to me. I will provide you the credential for limited space. You can upload your data set approx 2 to 3 GB. So that can be possible from our side. So when you want, you can write to me. I will provide you the credential. Okay, Sunena, I think no more questions.
Sir, I think she has one more question. She is still raising her hand.
I can see Sangeeta and
Okay, she has lowered down her hand. Oh, if nobody has any other questions, we can end the session.
okay.
Thank you so much, sir, for such a detailed session. I think we are all truly grateful for your knowledge and expertise. Sir, please share the slides with us
Okay.
so we can refer to them. Thank you so much, sir, for joining us today.
Okay, so thank you, Sunena, for this nice interaction with the participants, those who are working in the deep learning environment. So I will share my PPT also, and if anybody is interested, so they can write me for the internship and all. So I will provide you the my expertise is GIS and remote sensing, deep learning, CNN, and UAVs. So you anyone is interested, they can join our institution or our lab also. Okay, Sunena, so thank you so much. Now I can leave.
Yes, yes, sir. Thank you so much, sir. I will also share this email ID with on the portal. Thank you very much.